Okay, so thanks for listening to an experimentalist, and sorry for I will not be very precise in many of the things, but I want to show you that maybe what can be done in an experiment, and also show you what are the limitations that you can learn from these experiments. And I will not talk about the things that Alessandro was talking about, because I decided I will maybe scratch it a little bit and we can discuss it. I've talked about that too many times. I will try to talk about something else, which means that, if we measure, correlation functions, and what can you, if we take measured correlation functions, what can you learn about the many-body problem that you have there? And I think that's a question also that gives you a way of looking at it in such a way that I think gives you a uniform way of also determining what is in the data that you can take, and so you don't overinterpret what you see. So in a cold atom experiment, we do experiments with cold atoms. In a cold atom experiment, the thing that you have is that what we do, we take pictures. Let's start from there. We take pictures, and if you take pictures, the best thing you can do, you measure every single atom, every single constituent of your field that you want to look at. And you can do that either, in situ, which, got a lot of press, because, you can see every single dot is an atom, and because you know where they are, you can reconstruct where they are. Or you can do that in momentum. That's a picture from one of our experiments. Every dot is a single atom here, and it has a detection efficiency of an atom here, and here is about the same. Here you measure in situ, here you measure in momentum space, and that's, say, a picture of about 80 atoms here and 80 atoms here in an pair source from a parametric matter wave amplifier, and that's the atoms that sit in the original state there, and that's the first transverse excited state of a trap. So you can play around there. You take these images, and now you have to interpret these images. And what are these images? These images are basically single shot realizations of an endpoint correlation function. Now, if you want to get all information out of this endpoint correlation function, there are about 800 atoms in there. You very well, you will see very quickly that you never have any chance of getting all the information out there. I will show you, 4.6 point up to 10 point functions, and our 6-point function already has 6 terabytes. Yeah? And for an 8-point function, we cannot calculate and store anymore all of that, and for the 10-point function, the same thing. So you just simply don't have the resources to get all the information out of these images. Now the question is that what information can I get out there, and how can I get out there, how can I get the information out there, and what can I learn from this type of experiments? It's basically a thing that you would need the exponential resources to get all the information out of there, but of course I only have polynomial resources, and I will have to be able to look at things that I can get out of these experiments. So most of my talk will be rank about what type of things can we get out of the single shot realizations of an endpoint correlation function. So the thing is that where I want to start is from an old statement of Schwinger in 51, where it says, if I know all order correlation functions, I know my model. And of course, that would be fantastic if we can do that. If we can measure all order correlation functions, I can get out what I want for my system. But in practice, and as I said, in practice and observer, I can only measure a finite number of these correlation functions. And one example is that I want to get out these correlation functions that maybe allow me to describe the quasi-particles and their scattering properties. Yeah? And so to approximately now get a solution, or to approximately know how to write down a many-body problem, so to approximately solve such a problem, I want to find the degrees of freedom where only a very few, or the lowest order correlation functions are relevant, have relevant information. It means that all higher order correlation functions within the statistical accuracy of my experiment I can reconstruct from the lower order ones. And most of my talk will go about that thing, that how can we do that, and which correlation functions to use, and how can we quantify that, and how can we see that, to which order of degree, to which order of correlation function is the data is sensitive to. And of course, if I can find a set of parameters, a set of observables, where I can show that the correlation functions factorize. I basically have something like that I have an observer where I know that the Hamiltonian will be diagonal or will be approximated diagonal. In any of experiments, of course, I can only say that, I can approximately factorize a system so that Hamiltonian will approximate the diagonal. So I will basically try to go to that in a different ways and show that how you can implement that in an experiment. So I will first talk about the system we look at. Then I will talk about which type of correlation functions do we talk about, and how are they related to various parameters of a model. And then I will give a few examples. I will talk a little bit, very shortly, about the generalized Gibbs ensemble and how that's characterized by these correlation functions. And then I will tell you how can I quantify this fact if correlation functions factorize or not. And we'll discuss it in detail in the form of the Sine-Gordon model and experiments on the Sine-Gordon model. And in the end, I will talk a little bit about what happens if you quench from a Sine-Gordon model where you have, topological different vacuum states and things like that into a free system, and what happens there. And in Outlook, if I have time, I can give a few teasers for theories where there are experiments that give things that are not understood. So the system we look at is the weakly interacting 1D Bose gas, which you put in a trap, and to make it one-dimensional, you have to get all the parameters like the temperature and the chemical potential much smaller than the transverse level spacing. Then you basically sit in the ground state and you can ignore transverse excitations, and then your physics becomes one-dimensional. Yeah. So if you have that, and if it's a weakly interacting Bose gas, you can describe it, in a Mickey Mouse-like model with a fluctuating density, which is nearly uniform, but it's in flux. You can have a fluctuating density in the fluctuating phase. The system can describe the order parameter within the fluctuating phase and the fluctuating density. And these things are usually thermally populated or populated by quench or whatever you want to do. And what's nice in this, if you take a one-dimensional system, this fluctuating phase, you can measure the interference pattern. So most of the things that I will talk about are basically related to this fluctuating phase and how to measure this fluctuating phase and how this is related to. And of course, if you have a simple system like a one-dimensional system, then the fluctuations in the phase and the fluctuations in the density are related to each other because they're the two quadrature components of the quasi-particles that I have in the system. Yeah? Now, it's interesting because, one-dimensional Bose gas, you have also exactly solvable models. In principle, it would be the Lieb-Lininger model. But if you have a weakly interacting gas, you can write it down as a Luttinger liquid model, which has it's a quadratic Hamiltonian, and its excitation of sound waves. So it's a very simple system where you can test some of the concepts that you have in there. And if you take two coupled one-dimensional systems, you can write down, this system can be written down as a Sine-Gordon model, and then you have a non-trivial, non-quadratic term in the Hamiltonian, and that gives you other things that quasi-particles have a mass. You have interaction between quasi-particles, you will have non-factorizable correlation functions. So it's a very rich system where we have a good understanding about the models of the part, and so if we can look at these experimental parts and look at these fluctuations and measure these fluctuations, we can relate them, what we can see in the models, and get the different rights of the models. Now we do all these experiments, that's my only experimental slide really, we create a one-dimensional system somewhere on a chip, and we can create them in a way that the temperature is very cold, is about 1/10 to about 0.7 h per omega, so it's very deep in there. The chemical potential is much smaller than the chemical potential can be in the order of the temperature or smaller. And so we are in a regime where we really are in this one-dimensional regime, and it's done on an integrated circuit that tells you to do that, allows you to do that. It's very robust. You can do thousands and thousands of experiments to really make statistical things. So you will see tens of thousands of experimental shots where you can do really statistics on it.
So
yeah.
The chip has many
there's many wires and there are many things on it to manipulate it. And for us, it's now, I can make a very elongated one-dimensional system that is hundreds of microns long, and it's about a few hundreds of nanometers transversely.
So my question was, you needed all this lane to do the things, or just?
You need most of the lanes just to prepare the initial system, you know. Of course, there's many more other things on there you can do on the chip. And another part in that experiment, what is important for us is that you can take, you know, if you look transversely, you have an harmonic oscillator in a transverse direction, and we can very simply, by coupling to radio frequency fields and to the internal states of the atoms, change this single while into a double while, and we can make two of those systems, and these two of those systems, he can interfere with them, and he can measure these interference patterns in a very nice way, and this works in an extremely robust way, so you can really make statistics on that. So most of the things you will see will be based on interference patterns that measure the relative phase between two of these one-dimensional systems. Yeah? So now let's look at that, what can we learn from this? What do these, if you measure these interference pattern and calculate correlation functions, what does that mean? I mean, the simplest things in the trap, first of all, we work on the trap. Because we work on the trap, our correlation functions are non-translation invariant. Yeah? That's one of the problems. Yeah? So they're non-translation invariant. Yeah? And if you take the non-translation invariant correlation, so I cannot write the correlation function of Z1 minus Z2, but I have to write the correlation function of Z1 and Z2. Yeah? That would be very important. That would also be very important that it tells you, gives you a lot of information about the system. Yeah? And then, if I write down the correlation function like you would write them down for the field operators, you can show that if you are in a weakly interacting regime, and if you can neglect delta nz, but only if you can neglect that, that's related to this correlation function I can measure, because I measure the phases. Yeah? And so this correlation function of the field operators, it can then be related to the correlation functions either I phi of z1 minus I phi z2. Yeah? And in the higher orders, you can also show that the fourth order correlator can be measured by looking at this exponential here. Under the circumstances that this delta nz, you can neglect the density fluctuations of the system. There's other correlations. Of course, you can look directly at the phase, because we measure the phase, so why not making a correlator directly on the phase? You can do that too, but it's much more complicated experimentally, because, you know, if the e to the I phi, I don't have to take care about the 2 pi's. Yeah? But if I do the directly phase correlators, I have to take care about the 2 pi's. I have to be able to reconstruct 2 pi's. Yeah? But what's very interesting is that if I do the correlator directly of the phase, I directly get into the I get these correlators are directly linked to the quasiparticles. Yeah? So basically, if I do the correlators with e to the I phi, I get something that has to do with the field operators. But if I do the correctors that are correlators of the phase directly, I directly look at the quasiparticles of the system. Yeah? And then if I do the higher order correlators, you find that the fourth order correlation function is then related to quasiparticle scattering. The sixth order correlation function is related to 3 to 3 scattering. It's like and higher and higher.
Are you telling us you measure P directly?
Yes. We measure these things directly. That's what we directly measure. So basically, if we're able to measure to reconstruct the 2 pi's and measure these phase correlators directly, basically you can look at the quasiparticle scattering in higher order of these types of terms.
Why are the phases related to the quasiparticles? What is the explanation?
What?
Why are these phases directly related to the quasiparticles?
I mean, you can what the phonons in the system do. They have 2 different density quadratures, 2 different quadratures. Like if the photon has an x and a y quadrature, like in harmonic oscillator, and the phase is one of those quadratures. And if you measure them, you can show if you measure them directly, the phase, you can relate that to the creation and annihilation operators of the quasiparticles. Yeah, I have to tell you, I did not do that calculation. That's what my friends in Heidelberg did. And they convinced me and showed me where it's in Ginsterstein, how the pages are, where you can look it up. I trust them, you know. So let's first look about...
Wait, my question is how you measure directly P?
That comes directly out of the pictures we take. We measure the interference pattern, and then what we can measure is the phase of x and the phase of x prime. Yeah? And you can measure the phase differences between, you know, the phases, you have a gauge degree of freedom. If you add an average phase everywhere, it doesn't really matter. It drops out all of these things. Yeah?
The phase is defined up to 2 pi.
Yeah, indeed.
No, I will show you. If you measure the phase at 50 points, yeah, and if you don't have any jumps in there that are larger than 2 pi, I can reconstruct the 2 pi's. I have to do that. That makes it very difficult. That makes it, you have to have much, much better resolution to do that than to do the e to the I phi. Yeah?
But there is no physical operator in which phase would be directly present. It is always present through the exponent.
In local observables.
Yeah, in local.
Yeah.
Okay, so let's first look at the generalized Gibbs ensemble and this quasi-steady state of a nearly integrable system. So we did a lot of these experiments. That's what Alessandro also looked to, where we take a single one-dimensional gas, split it into two, and if you coherently split it, you basically make a copy as good as quantum mechanics allows you. But this quantum quench of the splitting puts some additional energy in there that starts a non-equilibrium evolution of a dephasing between the two systems, and you can look at that either in the full distribution function of phase and contrast, or in the phase correlation function of the system, and you can observe this type of things. The basic plot is that it can be seen. What happens is that if it calculate the mean squared contrast of this interference pattern, you first find a region which is very fast, which is a very fast degree of mean squared contrast. There you have a light cone-like evolution in the system, where you basically see that the local correlation function emerges locally immediately, and you have outside the light cone, you have a long-range order that stays in there. Then you get to a state which is a quasi-steady state, and I will talk about that, which is described as pre-thermalized state and described by the generalized Gibbs ensemble. And then you find a very slow further evolution, which can be related to phonon-phonon scattering and something, and that's very preliminary still, but it looks like that we see the right scaling laws over about 2 orders of magnitude for this decay rate, depending on this nonlinear relaxation model of phonons. Now, if I have this integrable system, and of course we have never have a perfect integrable system. An integrable system that has only quantities that are nearly conserved, I would write down, and I could write down now in a simple experimental way, not as nice as it was done yesterday, a way that the density matrix will have you will have a Lagrange multiplier for every conserved quantity, and so basically it means you have every Lagrange multiplier for every mode of our system. Now the question is that if we can measure this density, can we find out these Lagrange multipliers and measure them? Now, here is an interference pattern that you measure, and out of this interference pattern I can reconstruct. Now we do that in a simple way, these e to the I phi correlators. We can extract the phase, and then I can construct the non-translation variant correlation function. Of course, at the diagonal, this is Z1 equals Z2. The correlation is always 1. And then you basically measure, get that point, and from here and here it would add to here, from here and here it would add to here, and you can reconstruct. You make hundreds of these interference patterns, and you can calculate this correlator, and you can reconstruct this correlation function. Now, if a correlation function looks like that, it looks a little bit strange. Then what does it mean? It has a maximum in the anti-diagonal here. It means it has enhanced correlations if Z1 equals minus Z2. Yeah? And if enhanced correlation is Z1 minus Z2, it tells you that you have enhanced correlations outside the light cone. This is something that cannot come out from a standard fast quench. It has to come out from some much more complicated quench. Now you can tell yourself and say, okay, can I take this correlation function and make a model of a gas in an harmonic trap? I know my phonons, I know my excitations in there, and what would be the occupation numbers of these excitations to get this type of correlation function? So I can take that and I can make a model, and I say, okay, I want to know how many of these phonon modes can I really extract out of my measurement. I can say, okay, I only say I fit one phonon, the lowest phonon mode, and keep all the other ones constant. And I've tried to fit 2, I try to fit 3, 4, until about 9 phonon modes, and keep all the other ones with a constant occupation, and you can find your statistical significance, and you find that you basically, what you get is that you can get something like information out about the lowest 8 Lagrange multipliers. Statistically significant information about the lowest 8 Lagrange multipliers.
Which charges are you employing?
What?
Which charges are you employing for this Lagrange multiplier?
These are the mode. This is the lattice liquid. It's basically the occupation numbers of the modes. The very simplest model.
You are talking now about the single chain, right?
Okay, I cannot do the experiment on a single chain. What I do, I make 2 chains, and then I interfere them. And if you make a symmetric quench, then both have the same statistical properties of their fluctuations.
But
So it's
this is the
independent.
this is the Saint-Gordon.
No, it's not Saint-Gordon here. These are two latential liquids. So it's a single chain, basically. Yeah, it's a single chain. It's a measurement is a little bit more complicated because I don't have a local oscillator, perfect local oscillator I would have in quantum optics like a laser, which I can beat the other thing with. I beat 2 fluctuating systems with. So that's a little bit from the way of analyzing is a little bit more complicated. Yeah.
It's the mode occupation of the difference of the 2 bosons in each
Yes.
of the 2s.
Yes. So it's basically what's underlying is there that that because these are 2 integrable models, that the sum of the all the original excitation are in the sum mode, and we observe only the difference mode, and that's only what the quantum quench does, and that's what we look at.
And this data is for a fast quench? Where
It's this data is not for a fast quench. It's flat. Yeah. Yeah. So this data is for a quench where we first go slowly and then disconnect. Yeah. It's for a more complicated quench.
So in the interim part of the quench, you really have a Saint-Gordon.
In between, yes. In between you have a Saint-Gordon, and I will come back later on. You know, the problem is we didn't publish this for 2 years because we wanted to know why these 2 modes are higher, and we couldn't manage to do a calculation to show that. I think now, from some completely new data, which will show you all the way in the end, we have a hint why this happens. It is a breakdown of the Saint-Gordon model, I think, for our system. But it's not. So what you basically have is you have certain modes which are very low occupation and some modes which are very strongly occupied. And this mode is a mode which corresponds to a quadrupole oscillation of the system. Now, the other thing that's interesting in there is that this line 0.5 is the one what quantum noise would give you for an infinitely fast quench. And everything that's below there means you have entangled modes and squeezed modes, yeah, between the 2 systems. And so basically means that you create very funny quantum states, which would be interesting to look at afterwards, what happens in that type of system. Now, the next point is that if this is really a generalized Gibbs ensemble, I should be able to calculate also higher order correlation functions from that ensemble and compare them to what we measure. And this is, you can take your system and take a 4-point function, a 6-point function, a 10-point function. We just took now slices out of that. And these are the measured 4-point, 6-point, and 10-point functions. And these are the calculated one from the GGE. So you basically see that up to very high order correlation functions, the GGE gives you the correct type of prediction for the correlation function.
The higher point function, what are you plotting?
Now, I cannot plot a complete 4-point function. I keep two of those 2 points fixed, and then plot 2 other ones. And for the 10-point function, I keep 8 fixed and plot 2. And I cannot, as I tell you, this 6-point function, if I would plot it completely, has 6 terabyte. Yeah, that starts to get, you know, it takes much longer to do the analysis than to do the experimental data. Yeah, to take the experimental data in that point of view, because it becomes extremely complicated to calculate this high order correlation function. Nevertheless, you know, you see they have not very much noise, which is nice. If you have enough data of good quality, we can calculate them in some way, which I was shocked. I was shocked because I thought about, oh my God, 4-point function. If we can get 4-point function out, it would be fantastic. But then it turns out to be, you know, now how much information really in the 10-point function is, I will go back to it later. Yeah, but at least it comes out to be a nice. It looks out, you know, a nice thing. So from the generalized Gibbs ensembles, basically this. If you do finite quantities, you can put correlations into things outside the light cone. And this 8-mode model really describes nicely relaxed state. This 8-mode model also describes in a beautiful way the approach towards the relaxed state in there. It's not completely perfect because this approach assumes that all of them have the same phase in the beginning. So maybe you can use that as some kind of a tomography to reconstruct the state after the quench. That's, so to speak, for a generalized Gibbs ensemble. But what's also nice in there, it tells you, this type of analysis tells you that, of course, there are going to be many, many more modes that are, if you would have a perfect experiment, you would need many, many more Lagrange multipliers to describe the system, but your experimental data only is valid, or it only gives you information for about 8 modes, the lowest 8 modes, and we know, and it also makes sense that it's lowest 8 modes, because all the other modes that have higher frequencies start to produce structures that are in the order of our resolution, so they get swamped out, and also because they have higher and higher energies, the occupation numbers go down very, very much. So it basically tells you that, okay, you have some kind of experimental data, and even though a GGE would have many, 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 many more Lagrange multipliers, the real relevant ones to describe your data are the lowest 8 for us, for this example. And you always have to take that into account. What can you get out of the data? And okay, now this was, as I showed you, we can measure this correlation function. We can measure the higher and higher order of this correlation function. Now the question is that, do these correlation functions factorize? And how do we characterize that if higher order correlation functions factorize? Let's look at statistics. So basically, you can characterize the factorization of correlation function by something that's called the connected part of the correlation function. And the lowest order connected part is the variance. And for Gaussian fluctuations, all higher order connected parts, that's basically the fourth order correlation function minus 3 times the second order correlation function squared should be, is the connected part of the fourth order correlation function. That should be 0 if there are Gaussian fluctuations. And the same thing, you can write it down for the 6 and for now. I wrote it down for a very simple way that I don't have the indices. Otherwise, this would be completely, you cannot see what is in there. And you can take that a normalized way of this connected part, which is called the kurtosis, which is more or less you take that, divided by that, subtract -1. So basically, you get it different. And this kurtosis is usually 0 if you have Gaussian fluctuations. Now, if I want to do this connected part, and if I'm interested in quasiparticles, and I think the physics is in the scattering of quasiparticles, I can look at that. What happens if I take these type of correlation functions? I can calculate the second order correlation function, and if I write down the second order correlation function in form of these phase differences, I find that the second order correlation function contains already all order connected parts. So if I want to learn something about the connected parts of the phase correlation, this is a bad choice. And I think many, many confusions about physics of higher order correlation functions come from that people use exactly that way. All these connected part of the real physics already enters in the lowest order correlation functions. And then you can end up with a mess. So if I really want to look at correlation functions, the correlation functions we used in the GGE paper would be a mess. We cannot get anything out because we assume that the physics is really in this connected part of these delta phi's, and because they are related to the quasiparticle scattering, to the physics of it. Yeah? And so even the second order correlation function would have all order connected parts of the physics in there. So this is a bad choice of doing that. Yeah? So I have to use different correlation functions if you want to get the physics information out there. Yeah? And of course, if I have Gaussian fluctuations, who cares? All of these are 0, and then it's fine. If I have Gaussian fluctuations, it's fine. But if I don't have Gaussian fluctuations, I have to get I have to really think about which correlation functions do I use if I want to analyze that.
You are saying that if you compute that, the previous slide.
Yeah.
So the expression contain all order connect part. This is big theorem. What is it?
No, the Wick theorem would be Wick theorem would be that the higher order correlation function I can get out of the second order correlation function.
What I mean is the expression you are using there in terms of all this power.
Oh, no, this is just calculating what the second order correlation function, if you take this here,
Yeah.
if you write it down in form of the phase correlators delta phi, you find that all order connected parts are already in the lowest order correlation function for this e to the that's because I do this e to the I phi here. And you will also see later that some of the things we see in our correlation functions you would not see if you use that.
So this is just a generating function for cumulants.
Yeah, yeah.
But so in theory, I guess one can compute exponential where you have a parameter alpha in there, and then in principle you have access to all cumulants, right? So this is still a good thing to.
Yeah, but if I do an experiment, I have an error bars on there, and I would never get anything out.
Just want the first.
Yeah,
cumulant.
I want to see that what are the simple things I can extract, because you will see that if I go directly on the phase correlators, not this e to the I phi, but directly the phase correlators, it's before harder to get out the phases, but then I get the physics directly. Yeah, and you will see that there are certain excitations in the model, in the Sine-Gordon model, which have 2 pi phase flips, which are completely masked in that. They're completely gone, but I see in the other one. Yeah, so you miss a lot of physics if you use these ones. Yeah, so I only want to say that if you want to see what are the things I can get out of an experiment, I have to be very careful which type of correlation function I use. It's the same experiment, it's the same picture, but it's a different evaluation. Yeah. So we do that in form of the Sine-Gordon model, and we can access the Sine-Gordon model when we take a single well and split it into 2, somewhere in between. You have a tunnel coupling between the left and the right case, and then you have the Latinger liquid Hamiltonian with the phase and the density fluctuations in the quadratic part of the Hamiltonian, and then you have this non-quadratic part where you have the tunnel coupling and the density and this cosine phi field in there. And I don't like to write down the Sine-Gordon model in the normalized quantities because I want to write them down in these quantities that I can measure. Yeah? Yeah? I don't want them written down. I would don't write them down in this normalized quantity, but I think it's confusing if you compare it to that part. And then what is nice is that in the experiment, I have something that I can measure, which is the phase coherent length and the spin healing length. And I can characterize the strength of this non-quadratic term by this parameter q, which is lambda t over Lj. So it's a very nice way I can characterize that. And this is experimentally accessible parameters, and I can basically say that if you will see that I would characterize now everything by q, which is the relation between the phase coherent length of a single system and the spin healing length of the coupled system that characterizes this parameter q. I can look at that. So of course I don't have to say that here. A Sine-Gordon model, it can be mapped on this massive tearing model, on the Coulomb gas, or on the XY model. So I think it's an interesting model to look at and has very many implications. Now, can we observe this non-Gaussian measure? As I said, we're gonna take a correlation function, which is now the correlation function of the phase differences directly, and then I can make the correlation function, the fourth order correlation functions of this phase difference directly, and I have to reconstruct that. Then I can reconstruct, if I have these patterns and I have good enough resolution, I can reconstruct the 2 pi's, and then this is a fourth order correlation function measured in a symmetric way that this is minus 15 micron, plus 15 micron, and then Z1 and Z2. Yeah, plotted the central part of this correlation function, and if I have no coupling of the system, this is basically completely 2 separated Latinger liquids. Then I have intermediate coupling, and this is a very strong coupling. This is basically 2 Latinger liquids that are coupled very strongly. So this cosine, I can approximate it. All of my system lives on the bottom of the cosine. I can approximate it again by an harmonic oscillator. Yeah, and then you see that this is the measured fourth order correlation function. And then I can use Wick's theorem and calculate. Can I calculate the fourth order correlation function from measured second order correlation function? You see that if I have no coupling, I can perfectly calculate the fourth order correlation function from the second order correlation function. If I'm very strong coupling, I can perfectly calculate the full fourth order correlation function from the second order correlation function at difference 0. And in between there, you see that the correlation functions don't factorize. There's a connected part, and this is basically a connected part that's left over. That's something that I cannot calculate. This is the fourth order correlation function that would calculate from the second order correlation function, and that's a measured fourth order correlation function. So you see in an experiment, you can see it directly measure this connected part of the correlation function. Yeah?
Sorry, I still don't get how you measure p squared directly. I don't get it.
No, you take an interference pattern like that. If you have an interference pattern, you get a picture. Yeah, where you have an interference pattern.
You can measure density, right? Density and interference.
Yeah.
Moment of the data.
Yeah, I've measured interference patterns. I measured density.
Yeah.
And then I take each slice here. I can extract the phase. I can make a plot, the phase phi and x. And I can get then here maybe something like that. Yeah?
Do you
Modulus,
integrate density?
modulus.
Integrate density over.
Yeah, no. You take that, and each of those things is a pattern. And this pattern I can extract an amplitude and a phase.
Okay.
Yeah? And then I can basically, I throw everything away, I only use the amplitude. So for each of those slices, and I have something like 40 slices, yeah? For each of those 40 slices, I get a phase. Yeah? Now the phase, usually I get the phase modulo 2 pi, but if the pattern looks like that, then I would say it would jump from here down to here further, and I know that the pattern looks like that. I know that this is 2 pi. I can connect it to here, and I get the complete phase evolution.
The point, you cannot see the jump because for your data are always continuous.
Wait, you will see the jump. If there's a jump, you will see it. In the pattern, you see there's no jump, but my computer gives me for minus pi is pi of the phase. The Fourier transform or something, whatever, that I use to evaluate the thing gives me that jump. That's what the evaluation from the phase gives me, but I know that the pattern is continuous, and I know that this is a 2 pi jump. I can connect it to here, and I know that the real phase distribution looked like that. I can reconstruct it. If I have good enough resolution, I can reconstruct it. Yeah?
Because in principle you wouldn't know whether it does like this.
It could be, if I have not good enough resolution, and my fluctuation would be so fast that they're much faster than you can have 2 or 3 oscillations in between 2 of those points. I cannot reconstruct it. Yeah?
Why is the phase is continuous?
It doesn't have to, because why should it not be continuous in the model?
Because if you have a Gaussian measure, the field is not a function, it's a distribution. Even not a function for a free field.
For a local free field.
Yeah? No?
I don't know. Maybe we can discuss it afterwards.
Just phi is always smeared over some.
Nature doesn't make jumps.
I don't know.
But doesn't make
Sometimes.
sense. But the point is that it's ambiguously undefined up to pi.
I
So
mean, it's experimental
I
resolution.
don't know how you can fix this ambiguity.
You fix a reference and then
You fix a reference, and if you have an average offset, it doesn't really matter. Yeah. In a way, how you construct it, if there's an average offset in there, if you put an average additional phase to all of those things, all of this drops out how we calculate it. So there's an overall. You can add an overall add an overall phase. It doesn't matter. An overall phase doesn't matter. It's only the.
But you can change locally. In Z1 I can add 2 pi, in Z2 I can add...
No, I will see it in the pattern, and I will show you something when something that happens. You see it. You see it.
Okay,
The experiment tells you when it happens. Yeah? Just wait a little bit. Yeah? Yeah.
If it is a difference of phases, you would say will be defined modulus or 4 pi. If it is a difference, right? If it is a phase, by construction, is defined mod 2 pi. If
Yeah.
the difference will be defined mod 4 pi.
Yeah, but I can, if I want to know, if I know that it's continuous, I can reconstruct it.
It's a matter of definition. If it is a phase, it should be mod pi, right? 2 pi.
But if I have say if I take, let's assume that, you know, a momentum kick on a particle, yeah, like you take an electron, have a magnetic field, you know, the effect of the magnetic field on an electron is to deviate, to change the trajectory of the electron classically. Quantum mechanically is to give a phase, you know, a phase which is linear with delta x, and that phase is linear with delta x, and it just grows from 0 to, you know, 17,545 pi, and I can reconstruct it in that way. Of course, you know, you can always put jumps in there in between, yeah, but just wait, you will see what the point is there.
Can I then just confirm?
Yeah.
When you write average of phi minus phi square, there you didn't put the jump. You assume continuity.
Yeah. Yeah. So now we can characterize it by this connected part, and so we basically take the connected part of the phase distribution function and plot the kurtosis, and you see again if you have the system completely decoupled, there's no connected part. If the system is very strongly coupled, there's a very weak connected part, and there's a strong connected part for intermediate coupling. Yeah. Now let's look at that in a little bit more detail. Can we get more out of that? So first of all, these are the measured connected parts, and now I take one point here, one point of this whole pattern, and really plot the full distribution functions, because, you know, correlation functions are completely related to the full distribution functions. The same information is there in all the moments of the full distribution functions as there is in the high order correlation functions. So you just pick the one which gives you the right information out there, which illustrates what you want to see. Now, first of all, you see if it's very strong, if it's completely independent, you see a very broad Gaussian distribution of the phase, of the phase here from this point. If it's very strongly coupled, you see again a very narrow, but it's still Gaussian distribution. And in between here, if I take a point here or a point here, you see funny distribution of the phase. And you see distribution of the phase, it's peaked at the center and at 2 pi and minus 2 pi. Now, if I would have used the e to the I phi correlators, this thing would be gone. I would not see it. Yeah? Now, what is that? We can take pictures, these interference pictures, yeah? And look at that. There's one interference picture, and it has a very small fluctuation of the phase. But then sometimes you have interference pictures that look like that. You have a 2 pi phase jump. And you can really see the 2 pi phase jump in the interference pattern. And what are these 2 pi phase jumps? These are kinks, these exit the solitons of the Sine-Gordon model. So you see them directly. Yeah? So basically, this kurtosis, or this non-factorizing part of the correlation function, tells you directly that you have this type of excitations in the system. Yeah? And you can see them in the full distribution functions, you see them in the kurtosis, and you see them directly in the patterns. Yeah? So these are these topological excitation of the Sine-Gordon model, and basically that tells you that you have different, that you have your system is here, it's cooled in a ground state, and it's cooled in a different vacuum state, which is vacuum state with one single Sine-Gordon soliton in there. So you basically can see them directly in the experiment. Yeah? And if I would use the e to the I phi correlators, I would not have seen that. But all these 2 pi's would be gone. Yeah?
Sure.
Yeah? Yeah?
Go.
I was just about to say, in Sine-Gordon, we often calculate the correlation of other operators like e to the I alpha phi for arbitrary alpha, and there I suppose we will see such a thing.
Yes, but that's...
But of course,
But we can go this and probably calculate these from the data too.
One thing to keep in mind, I think this is in the semi-classical regime, so beta goes to 0. So you have infinitely many breathers,
right.
yeah, so which are the phonons here, and then solitons at very high mass. So this is why there's so few.
Okay.
Yeah.
Should be should we be worried about the difference between experiment and theory?
The theory is for an box-like potential. It's not for an thing. And the theory, what I plotted here, is for a thermal equilibrium. And we cool into that system, and it's not completely clear that we cool into the completely thermal equilibrium, because these solitons are very long-lived. If we create them during cooling, they stay in there. And we definitely see if we cool faster, we have more. If we cool slower, we have less. Yeah? So there's a way of really, in a very clear way, looking at kinks that happen in the cooling or something like that. But this is all in a harmonic trap, so that makes the analysis much more complicated. Yeah. So the basic is that we get the right order of magnitude of the kurtosis, which is probably what you expect if you have average parameters. But how it really looks like in the long distance, it has to depend all of the details, and it basically tells you that the simple model that we did in here is not exactly the one that we would expect from there. Okay, so now we can do that in even in more details and make the 3 sigma upper and lower limits, and you see that really this connected part of the correlation function is really statistically very, very significant that you measure. Now the question is, what happens to the 6-point phase correlators? We can evaluate the 6-point phase correlator again, 2 times 2 symmetric points, and then you see that, of course, for the Wick factorization, you cannot reconstruct the 6th-order correlator from the second-order correlation functions. But now the question is that can I reconstruct the 6th-order correlator from the second-order correlation functions and the 4th-order correlation functions? So the connected part of the 6th-order correlator would be, this is the disconnected part and this is the connected part. And then you see that, okay, maybe there's a little bit that's left over, but it's mostly basically our data is not good enough to really get a clear signature that you need in 6th-order connected part of the correlation. So it basically means that our data we can describe mostly out of the the second-order correlation function and the 4th-order correlation functions. And the 6th-order correlation function is on the verge of it's something like 2.5 sigma or something. So it's a little bit something there, but it's not there. So now the question is that can we see that in more detail? Since we can see these solitons in the pictures, we can take these pictures away. And let's assume that we only take those realizations where we are in the real ground state of ground vacuum state, no solitons. Then do we see phonon-phonon scattering directly, or breather-breather scattering or whatsoever in the system? And you see that where is that? Sorry, here. So in that realization, for example, you find that if I take out the solitons, you see that these kinks are completely responsible for the difference between the Wick factorization and the full 4th-order correlation functions. And if I take out the soliton and see that this is a factor of 100 difference in the value of the correlator, you see that basically, okay, for this type of parameters, when they have a relatively large plasma frequency, that basically means your cosine is very high, and if you take out the solitons, you live in the lower part of the thing, that basically quasi-particle breathers are more or less don't scatter. All the non-factorizability of the correlation function is in the solitons. Now if you go to intermediate ones, you find you're left over with something. Yeah? You see that if you take the solitons out, you left with something, and you have a full distribution function of the phase, it looks like that. If you take the solitons out, you have a full distribution function of the phase, it looks like that, and that has 2 long tails, it's not Gaussian. And there you really see quasi-particle scattering in the model. So, yeah.
It's a stupid question, but when you say that the difference is very small when you take out solitons, you also said that the values were really, really small. So isn't it just because...
but it basically tells you that...
A relative difference.
The thing is that, okay, we're not good enough, the data doesn't have statistical accuracy to see it. Of course, there's always a little bit there should be always a little bit of a non-factorizable term left over, but the question is that how big is it? Yeah? So the data, or the way how we can do the experiment, is good enough to be described by a model which has, which is non-interacting quasi-particles plus, Saint-Gordon solitons. Yeah? Whereas in the other case, in this case, it's not good enough. You have to take quasi-particle scattering into account. Yeah?
So what are the tails? I mean, what kind of behavior do you observe in the tails?
I think it has to do that we have the, this is the cosine part, and then you live in here, and you basically, so you have, this is the phase phi, yeah? And then in one of those systems, you basically live there where you can approximate it quadratically. In the other one, you filled up, your system lives from the energy that's in the system, it lives up to here, and then you see that this is not a quadratic. I mean, in details, that would be a question really to find out what is the things that we see in there. Is this which type of scattering process are there? Can we connect that to really something that we can see in a theoretical model of that? Yeah. So first of all, we can measure correlation functions up to 10th order and more, but I think it's not for the moment in our statistical accuracy up to 6th order correlation functions. There's information in there. The higher ones are nice to show, but I think you don't get any new information out there. By the way, we're doing right now experiments about 20, 30 times the statistics. Maybe we can get the 6th order really out. Yeah, but it's a question of you need tens of thousands of experiments that are all in the same parameters. Yeah. These four distribution functions and the connected part of the correlation functions, they have the same information, but some of them are easy to be seen in the full distribution function. Other part is easier to see in the connected part. You can tell information about the quasi-particles, interaction of the quasi-particles, and the vacuum states of your system. And I think looking at these higher order correlation functions gives you really insight into the effective theories that describe this many-body system. And for our resolution, the 6th order is sufficient, and it's necessary to take, basically, would mean that if you take a perturbation calculation, up to 3rd order should be fine enough to describe the data. That's what we can see from the data, and it's nothing that the statistics can tell you, with limits and something what is out there. Now, the question is, of course, take the Saint-Gordon model and then quench into something free. How long does it take that the kurtosis goes away? And this is very preliminary, and we try to play that, and this is those parts, and you see after a few milliseconds it's gone. Yeah. So the system, even though the Hamiltonian is completely Gaussian here already, it takes a little bit time until the thing is gone. Now we can look at it. How long does it take? Is it that the quasi-particle rearrange itself, or is it that most of that is coming from the Saint-Gordon solitons, that how they decay? This is something we can now study in there. And this is either in the kurtosis or in the connected part of the 4th order correlation function. You see, this is the 4th order correlator, the big, and this is the connected part of the 4th order correlation function. We can look at it, how it goes down. Is there again a light cone in there and all this other stuff? We can look at that. But that's basically something that we will be in the next few months to look at that. So I think what have we learned on there? I think the higher order correlation function and these full distribution functions, and especially the question if they factorize, I think gives nice insight into the effective theoretical description of this problem. In that sense, it helps you, what are the solutions that you need to describe your data. It allows to identify interesting many-body quantum states, and it allows you to probe the excitations and the statistical properties. Good. If I have a few minutes, I can basically give out a few
5 minutes.
Yeah, if I give out a few teasers. Yeah. So this is not going to be complete, but it's going to be. First thing is that John talked yesterday about revivals. I will show you one. Usually, if you have a box potential. Oh yeah. Oh God, this is again my. You don't see how far it's filled up. You have a box potentials. You would expect that the realization happens with the light cone. This is the 2nd order correlation function, and if it's very high, have the long range order, and this is the light cone, and you would, if you had box potential, would expect to get a revival. If you have a harmonic trap, you don't get the revival because you don't have any equidistant spacing of the phonon frequency or equidistant spacing of the thing. So basically, you can measure very nicely the light cone that I showed you before, but you don't see the revivals. Now, of course, it would be great to make a box, but as experimentalists, we can make a cheap way of making the box, and that's you add walls to here, and then it's not a perfect system, but then this system looks like that. So you see the light cone, and you see one revival, maybe a little bit of a second revival, and it's gone. Yeah. So it's very, very. So basically, that's an experiment with 5,000 particles, and 5,000 particles you see revival of the contrast. Yeah. And so we're working on it and making the box nicer and doing that, and it's yes. So I think we should be able to really measure this and see this, look at this, at least for the simple one-dimensional system, to look at that in the case.
Can you make the box by Fourier?
It's underway. Don't worry. in a year, you will have a box and something that's 5 times as long, and you can make Fourier analysis, everything else. If it works in a nice way. I think it's going to take us. We're going to see many imperfections in the experiment first. What we see already there is that you start seeing shock waves from the phonons being excited. If it's not perfect, the walls or something, there's many other. It would be great to make a a ring and make a periodic boundary condition, but that's it's much harder. The box is simpler to do. Yeah. The next thing is that the question is that we talked about the Saint-Gordon model, and we looked at that. If you can initialize a Saint-Gordon model with a specific phase difference, you can basically take a single well, split it coherently, add some phase difference, and connect it together. Now, then you would expect to have a nice Josephson oscillation. And if the Saint-Gordon model is perfect, you would also assume to have a good this oscillation. But what we always see this type of spirals, and see everything goes down to a fixed point, and it's like, and this fixed point is basically phase 0. So basically phase locks, the system phase locks. Now, if the basis of the Saint-Gordon model is that the symmetric and an antisymmetric mode don't couple to each other, this tells you that there's some coupling to it. Now, this is again an harmonic trap that might have to do with the trap. Yeah, but we can look at it, and there's a very simple phenomenological model, but not for the two coupled 1D system, but you add some kind of damping, and if you do that, you can describe it. But it's not very nice just to put some phenomenological thing in there. It would be nice to understand what's the physics of that, because that would be very important to find out. How long is the Saint-Gordon model really valid for that? And is it's a trap, or is it really the physics of interaction between the symmetric and antisymmetric modes in the system? And the experiments are done by Marine. You can invite her. She gives very good talks on that. And we started talking to many different people, Thierry and Eugene and others, and we try to solve the problem. And it's also, we can look at that, if you go outside, if you are outside the separatrix, you should stay up there, you should be self-trapped, and we see that you're not. You see a decay of the self-trapping, and we can put some effective parameters in there, and that's also okay. So you can look at that. There's many types of things we can look at, and I think it's a very open problem and has many different things to start. And the third teaser is, I said we can have systems, 1D systems. Now the question is how do we prepare them? And didn't tell you how to prepare them. And usually we prepare systems, and you take you do that with evaporative cooling. So you take your distribution function of occupations in your trap, and you throw the highest occupations away, the highest energy atoms away, and then rethermalize. Now this doesn't work in 1D, because in 1D, if I'm really cold, to do that, you need thermalizing collisions. And in 1D, these two-body collisions can only contribute to thermalization if they lead to transverse excitations. Now, when do they lead to transverse excitations? They basically means that they have enough energy to excite the transverse state. And so these thermalizing collisions are exponentially suppressed by Boltzmann factor, by e to the minus 2h per omega over kBt. Now the mystery is that we get down to 0.1 h per omega in the experiment. It basically means that factor is e to the minus 20. How the hell can we get there? Yeah, it's an integrable system. There's nothing. And you see that what typical experiments are, there's these, depending on where you go, and this 10 nanokelvin here corresponds to something like 0.08 H bar omega. Yeah? In our system. So we can get very, very cold, but how the hell can we, we throw atoms out there and we get cold. Now let's look at that in more detail. If you take a system, and a one-dimensional system, and let it expand, you see a speckle pattern. This speckle pattern tells you the phonons, the phase fluctuations that are in the system. Now if you outcouple atoms, you see that the outcoupled atoms have exactly the same pattern right there. So it basically means if you outcouple atoms, and they also take excitations with them. Now when they take excitations with them, they basically means they reduce the density fluctuation of the system. Remember, density fluctuation and phase fluctuations are two quadrature components of the phonons. So I can write them down. I can write down the Wigner functions. And basically what it does is that the Wigner function of the phonon distribution rotates. And this cooling squeezes them in that one side. And it's like a potter's wheel. So we could squeeze them and they get narrower and narrower and narrower. And that gives a very simple semi-classical model. And that semi-classical model predicts temperature T over T0 is n over n0, and all the data fall on one part. And whenever we do experiments, they fall on this. You could think, okay, great. That explains it. There's one caveat in there. The semi-classical model completely neglects that when I outcouple atoms, I should get quantum noise in the system. And if you do that, it doesn't work anymore. We don't know why. We ask everybody, I don't know, who's the theorist who came into my lab the last 2 years? Everybody was asked the question. Nobody found an error in the calculation. That's why in the end, we put it on the archive, and the experiment's coming out next week, on Monday. Yeah. Our theoretical calculations are on that paper with Piotr, who now works with Thierry. It shows that, if you put it in quantum noise, it doesn't work. Maybe the semi-classical model is wrong. Yeah. Maybe, if you output couple very, very weakly, you put in much less quantum noise than you would expect. Because if I split very slowly, I can also, suppress the noise fluctuations between two condensates. We didn't figure it out. Would be a nice way of, we can discuss it.
The importance of higher order scattering modes, because you say two.
That the thing is that in 1D, it's a very good question. In 1D, we are in a regime where mu, the chemical interaction energy, is much smaller than h bar omega. The time scale for an atom to leave is 1 over omega, and the time scale to scatter is 1 over mu. So the atoms don't rescatter when they leave. Yeah? If we are not in 1D, of course, then you have all this other junk. If we're in 1D and we start in a regime where we have all these experiments are done in a regime where we really start already in a very deep in the 1D regime, and we can still cool further. Yeah? So there's no high order scattering, no higher or rescattering. They should not be in there. Yeah, that was our first thing. Then we thought about that, and it's So yes, that's fine. So I told you that my experiment. So we have the experiments I told you are mostly done by Bernhard Rauer, Thomas Schweigler, and Tim Langen was involved in there, and that Josephson oscillation experiment was the thesis of Marine, and she's about 2/3 done now. If you're gonna have to do that. And of course, there's lots and lots of theory contributions. I couldn't talk about the stuff we did with the ends, which was reconstructing these many-body quantum states. Maybe he can mention something of that. So using matrix product states to reconstruct these things. And yes, of course, there's lots of funding thanks to ERC. I can do these experiments. Otherwise, it would be tough. Okay. Sorry for being 5 minutes longer.
Okay, we had really a lot of questions during the talk. If there is something really urgent, I will allow it. Okay.
We can go for a beer afterwards, you know.
Jörg is here for.
I'm here until tomorrow late evening, so.
So just block him and ask everything you want to know from about the talk.
And you know, you're welcome to come into the lab and sit there and see that these things really happen, you know.
You know the effects of a theoretician in a lab, no?
No, some of them is bad. Yes.
Exactly.
But I have you know, Sebastian Erne, the theory student from Heidelberg. He spends half the time in the lab. He's really, because that's, you know, he does all these calculations in there, and it's good to have him directly there and to see what really happens, that these things really happen there, you know. So, no, I'm not afraid of that, you know. Oh, that's a lock, you know. You can only go from the outside. I'm also not allowed to go in there anymore.
Okay. Let's thank Jörg again and.